Welcome to the Maine Science Podcast. I'm Kate Dickerson. Today's episode is a conversation I had with Amber Whittaker, a senior geologist for the Maine Geological Survey. I had the great good fortune to hear a talk that Amber gave at a University of Maine physics colloquium, and even before she was halfway through her talk, I knew I wanted to have Amber on the Maine Science Podcast. Her passion for geology, learning, and working for the public good is so clear in our conversation, which was recorded in November 2025. I hope you enjoy it as much as I did. Today's episode is supported by Maine Technology Institute. MTI is celebrating 25 years of making grants, loans, and equity investments to businesses, organizations, and entrepreneurs to strengthen Maine's innovation economy. Amber, welcome to the Maine Science Podcast. I was lucky enough to attend a talk that you gave recently at the University of Maine Physics Department about your work. And I will say from the get-go, the part that caught the physics chair's attention is the fact that you measure gravity. So that's a whole kind of fun thing. But I've actually been a fan of geology and geologists for a really long time. I still remember taking a class in undergrad in hydrogeology. And if I wasn't a senior, I was like, oh man, this would have been a cool field to go in. So I was kind of hoping you could start with, how did you get into science? What was it? And some of your background, and then we'll talk more about your work with Maine.
Yeah, thanks for having me. I think the way that I got into geology is probably similar to how most people get into geology, in that I didn't start college thinking I would be a geologist. I think for most of us across the country, at least in the US, geology isn't taught in high school, which is kind of when you're starting to think about what you want to be when you grow up, or at least when you leave high school. I'm not sure I've ever grown up. That's why I laugh when I say that. So when I went to college, I thought I wanted to work for the United Nations as an interpreter and travel the world and, make some kind of a global impact, contribute to global politics. I had taken a lot of languages in high school. I had taken 5 years of French. And so I thought, I think I'm good at languages. I'll go into translating. And so I started college as an international affairs major with a focus in German. And I was doing that for a long time. And this is the story that I think every geologist has. And then I took an intro to geology course. And I realized that, first of all, that I needed to be a scientist. And then second of all, that I was a geologist. And I had forgotten that as a small child, I picked up rocks all the time and was really fascinated with rocks. I love to climb on rocks. I think my happy place as a child was at Pemaquid Point, sitting on the rocks under the lighthouse. And I had forgotten that going to college, and this intro class really brought it back to me. And so then I switched my major to geology. And I think that that's the story that most geologists have.
Yeah, it's interesting because I think there's been a little bit of a change with earth sciences being part of the curriculum, I think, in middle school now, but it seems very cursory to me. It's not as quite the deep dive you get into in an intro to geology course. Before I let you talk more about your work, I'm curious, what is it about that class that made you say, oh, wait, I need to do science?
So I think as a young person, I don't think I knew myself very well, but I think part of the draw for languages for me was the problem solving aspect of it. So I went at languages as if I were solving a problem, right? So you've got two different words and you're essentially matching their meaning and trying to get a point across. And so I think I was really problem solving, because when it came time to have a conversation with a real actual person, I would freeze up. I was not very good at conversation. I could translate anything, and I still can. I can read and kind of pick out vocabulary for French and German. But trying to have a conversation with someone, I just freeze. And I think, I'm introverted and I'm anxious, and that's not the part of language that I like. It's doing the work. It's the data. And so I think that was one of the things in taking this class was, I need to be working with data. I really like collecting information, analyzing it, processing it, and then making a story with it. That's what attracted me to science. But then geology in particular, because of course I had taken other science classes and I hadn't captured my imagination as much. Again, growing up in Maine, you spend a lot of time outside in the outdoors. And I think you kind of have an appreciation for the natural world. And then going into a geology class suddenly explains that natural world, and you get a story about everything you're looking at is actually telling you information. It's telling you about its history and how it formed and what it's doing. I think that clicked for me as well, because I had always been appreciative of nature. And then this gave me like a reason why things were as they appeared. So those two things, I think, is how I got attracted to geology and science in general.
So how did you end up in New Mexico then? I know they have rocks too.
They do, and you can see their rocks.
You can see them. It's a lot easier. They're not quite so hidden, but it is a very different landscape, geologically and otherwise. Was it that drew you there, or was it something else?
Yeah, so I did undergrad in Maine. I went to the University of Maine, and you're kind of encouraged to continue in academia rather than kind of go out into industry to get a job. So I was encouraged to attend graduate school. And as you do, you apply to a number of places, because graduate school is really about your advisor and the project. So you have to find a good fit. What is the project going to be? What is your advisor like? So you apply to a few places and you go and visit and you just see what works for you. And so I did that. I think I applied to like 5 places and I visited them. My life could have taken many different paths. But when I went to Albuquerque, New Mexico, and visited the university there, that was just a better match for me. And I wonder if part of it is that New Mexico is really rural. Other places I visited were in big cities, and I'm not a big city girl. And I think that the feel of Albuquerque, even though it's a city, it still feels quite rural. And as soon as you get out of the city limits, there's like nothing. And so I think in that way, that suited me. And then, maybe how different it was attracted me as well. I mean, there's like no water there and the rocks are all exposed. You can see it, right? So you're in Albuquerque and the Sandia Mountains are there and you can see all of the rocks. So that's very exciting. And so that's how I ended up in New Mexico. So I did a master's degree and then I left for a while. My husband was doing his PhD in New Zealand. So I moved to New Zealand for a while and worked there. And then we actually moved back to New Mexico for additional graduate work. And then I ended up working there.
How different was it in New Zealand geologically?
Oh, geologically. It's geologically younger.
Oh, interesting. Okay.
Yeah. So there's volcanoes. There are active volcanoes. So that's interesting. So the geology in Maine is very old, right? And obviously we have no active volcanoes. And then you go to New Mexico and there aren't like volcanic explosions going on. It's actually still quite hot under New Mexico. And things are younger. So within the city, you can look out on the west side and see fairly young, geologically young volcanoes. They still look like volcanoes. You can still see the lava. I think they're like 100,000 years old. So very young geologically. And so I was kind of stepping it younger and younger, I guess. And so you go to New Zealand and obviously there are active volcanoes. I mean, we hiked quite a few of them. But it's interesting because it's kind of an analog for what would have been happening in Maine. So it is a plate boundary. That's why the volcanoes are there. There's also a major strike slip fault that's active. There's a lot of earthquakes that are associated with that. So those things that you can see happening in New Zealand, they actually happened in Maine just like 400 million years ago. So geologically, it's quite interesting to visit these other areas that are young.
Okay, we're going to jump time, get you back to Maine. Because you do work for the Maine Geological Survey, which I personally think is really cool.
I think it's very cool too.
Good. So we're in agreement on that. I'm going to go out on a limb and guess that most of the people who listen to our podcast don't know what that means in the sense of like, what does a geologist do for the Maine Geological Survey? And what is the mission of the Maine Geological Survey? And I realize that that is a lot. We could spend hours talking about all of those things, but if you want to just kind of give us a slice of what you do and kind of connect to why Maine even has one, that would be really cool.
So most states have a geological survey, or if it's not called a geological survey, something that fulfills the same function. And the mission of a survey is really to collect and disseminate fundamental information about geologic topics. And so I say that because geology is really quite broad. I look at rocks. I'm a bedrock geologist, but I am the only one at the survey. So there's also a superficial geologist, and that's really looking at the materials at the surface of the earth. So the sand and gravel, which of course is a major industry in Maine, right? Sand and gravel pits. And then in Maine, we have the glacial landscape. So our landscape was really impacted and formed by glaciers. And so we have glacial deposits. And so that's all superficial. But then probably the larger topics in geology that are important to everyday lives would be water. So drinking water, flooding, that kind of water. And then in Maine, coastal processes. And so I think we now have 3 coastal geologists and 2 interns that work with them. So we really have this giant for us coastal group. And then we have 3 hydrogeologists who are looking at water. So what I do at the survey is look at the bedrock, so the rock under your feet, and that is doing the fundamental mapping of those rocks. And it's kind of the same for surficial. We do the fundamental science of mapping those materials. And again, with the water or the coastal processes, we're really collecting foundational data that other companies wouldn't be collecting because it's not profitable, right? You don't profit from making maps, but everybody needs that if you're going to use it, if you're going to evaluate a piece of property, if you're going to make a plan for developing it or for infrastructure, that's data that you need. And so all surveys are kind of, the mission is to collect and disseminate that data, that information that everyone needs to use, but nobody has the time or the money to collect.
So it sounds to me very much like the definition of a public service.
Yes.
That is available for everybody to use. I'm curious, you can see exposed bedrock in a few places in Maine, but there's also places where it's fairly deep. Is there a consistent pattern? Is that part of what you're trying to figure out? Do you know what I mean? Like, is there something that you are able to have figured out and identified that you can make a blanket statement about Maine? Or is it similar to the coastal geologists who just had a talk, and I think part of the things they mentioned was that we have more miles of coastline than California? Or is it just so vastly different depending on where you are in Maine that you cannot make that kind of statement? I think what I'm trying to figure out is, how much do we already know about the bedrock? Is it something that you can make a statement about that says, we know this about Maine, the whole state? Or is it you are truly doing very foundational stuff and we can't even make that statement?
Yeah, so I can sort of do both. I can make a general statement that is, Maine's bedrock geology is extremely complicated. And we do know that, but the details we are still discovering every day. Every day a geologist goes out and does detailed bedrock mapping in Maine, we make discoveries that we didn't know about. So the whole state is mapped at very low detail. We do have a geologic map of Maine. And what we know from that is the rocks of Maine were assembled over millions of years of different plate collisions. So if you're familiar with plate tectonics, the crust of the earth is broken up into different plates, and those plates move relative to one another. They spread apart, they slide by one another, and they collide. And all of those things change the rocks or create rocks or destroy rocks. And that cycle has been happening for hundreds of millions of years. And so over geologic time, all of the continents have come together as one. It has broken up into little pieces. New rocks were created, and then those all came back together again. And then they broke up again. So like all the rocks on Earth have undergone quite a few events. And Maine has had like 10 different events happen to it. And so overall in Maine, there's kind of like a northeast to southwest trend of the rocks. And those are all from different collisions that happened to build up the rocks of Maine. And so we know that in a very broad sense, because as you can imagine, like a collision of rocks is really putting together many different rock types and squishing them and breaking them. And so when you look in detail, it's very, very complicated. It's also more complicated because of what you said, they're not exposed everywhere. So those little places where the rocks poke through the glacial deposits, those are the only clues that we have. And they are not continuous. It's not like out west where you can follow a contact between rocks for miles and miles and miles just from standing in one place at an overlook. That doesn't happen in Maine. So we are little Sherlocks trying to collect hints and pieces of evidence and then trying to create a story that makes sense. And every time we collect more data, we have to revise that model. So the general statement is Maine geology is very difficult, very complex, bedrock geology, and that we don't know it. So we have mappers going out now who are discovering new things. I discover new things all the time that aren't on that overall map of Maine.
Okay, I want you to hold that thought. I have one question, a slight detour. How unique is Maine for complicated 10-event geological impact? Like, are there other places that are as complicated, and do we fit in with them? Like when we all came together as one continent, are the places that are similar to us where we were attached?
Yeah. So, I mean, obviously, so our geology doesn't stop at the Maine border. It goes up into Canada. So a lot of the models of how Maine was assembled Those models came from Canadian geologists looking at Nova Scotia and Newfoundland and on into Ireland and England, right? So all of those land masses were once together before the Atlantic Ocean opened. Also Africa, right? And Europe, like all of these land masses were together. So the Appalachian Trail ends at Katahdin, but there's an international Appalachian Trail system. And that follows the geology. It follows the Appalachian Mountains, which are quite old. And those Appalachian Mountains you can trace through to Europe. And so the International Appalachian Trail actually goes across many different countries across the ocean. And so that's the similar concept, is there are places that have a very similar history to Maine. And that helps us try to piece together our own history, especially if those areas have better rock exposures. The other thing that's complicated in Maine is that we underwent a lot of high temperature and high pressure events that maybe other places didn't. And what happens to rocks when you do that is you can obscure some of the original history. And so by studying those rocks that didn't get melted or squished as much as ours, we can kind of say, oh, okay, our rocks may have once looked like that. And that helps us out. So we can go and look at what other geologists have done in these areas that we must have looked similar. And so we can bring it back home and try to apply that.
So it does give you, if not a starting point, things to cross out of what to look at based on what the other places have experienced or discovered.
Yeah, hypotheses to test.
Okay, I'm going to lean into a little bit of what you spoke about when I got to see you talk a couple of weeks ago about how you do the research to figure out what the bedrock is when everything is so covered up and you can't follow it for miles and miles like you can in the Southwest. I think that that's a good sense of what it takes to do this foundational science. It's a lot of hard work and it's a lot of problem solving, all the things that you said you like, but it's fascinating to think about how you do that. So if you wouldn't mind stepping us through that, I think that would be really cool.
Yeah, so when I do bedrock mapping, I do start at my desk first, kind of doing two things. So one, figuring out if any other geologist before me has looked at these rocks or at least has worked in the area that I'm going to be working in. And the answer to that is usually yes, to some extent. Geologists have liked to come to Maine since like the early 1800s. I mean, Maine, of course, has been a playground for the rich. And I feel like that was the same for geologists. They liked to come here. So we do have some old information about the rocks. Generally, they stuck to the roads because they were trying to cover a lot of ground. And so I can kind of get some hints by looking at their data. And so I do background research. And then the other thing that helps me is kind of new technology, of course. So the state of Maine is covered by LIDAR, which is light detection and ranging. So we bounce lasers off the surface of the earth, and that gives us very high resolution information about the elevation of the earth. And because it's so high resolution, it actually shows us textures of the ground surface. And so I can use this information sitting at my desk to say, I think there's an outcrop of rock there. And so I can plan my work in that way. So most of Maine, all of Maine, is privately owned. So the other thing I need to do is get permission from landowners to access their land. So I can look at the LIDAR and say, all right, this parcel of land I think has outcrop on it. And I will then write a letter to the landowner asking for permission to go walk their land and to look at their rocks. So that all happens before I go out in the field. So out in the field, you kind of go, and the tools I have with me are like a GPS, right? So I can have coordinates. I have my trusty hammer hanging off my belt so I can break rocks and get a fresh surface. Most rocks, of course, in the woods are covered in moss and lichen and stained. And so really to identify a rock, you need a fresh surface. So I'm forever just bashing at rocks out in the middle of the woods. I have a compass, but what the compass is doing for me is not so much navigation, but I am measuring the attitude of different features in the rock. And so that tells us about the structure of the rock. If you think about like the Grand Canyon, the upper layers of rock there are all flat and horizontal and pretty continuous. And in Maine, we almost never see that, right? Rocks have been folded and they've been shifted around and they've been tilted on their ends. And so we measure that orientation to let us know how the rocks are behaving under our feet in those places where we can't see. So I'm measuring those with my compass. I'm also probably taking samples to bring back to get chemical information in a lab or to cut them and look at them under a microscope. to help me identify them or help me figure out what's going on with the rock. So that's kind of the physical part. And again, outcrops are not continuous. They're few and far between. So I visit as many as I can. And then we try to apply some other techniques. And so one of them, which is the talk that you saw, is trying to apply geophysics. There are many different geophysical techniques that geologists use. For the most part, they are very expensive. And the Maine Geological Survey is actually not well funded. A lot of our work is grant funded, and we have to be very efficient and judicious in how we spend that money. And generally, I can't spend it on geophysics. But in a place like Maine, where I can't see the rocks, you really need to be doing something else to figure out what's going on. Again, my problem-solving superpower, I swear this is like what I'm good at, is I was trying to figure out, well, how can I do geophysics and how can I help myself and my contractors who also do bedrock mapping figure out more about the rocks. I attended a talk where a geophysicist was talking about ground-based gravity surveys, and they are fairly inexpensive to do as long as you can get a gravimeter, which is the piece of equipment. They themselves are very expensive, but he said that most colleges and universities probably had one languishing in their basement. And I thought, you know what? That's probably true in Maine. And it turned out it was. So I talked to a few of our colleges, and it turns out that Bates College had a gravimeter that none of the faculty were using. And so they allowed me to borrow it. And so what I'm hoping to do is use this technique to essentially image the rocks beneath our feet and to help me come up with a better story about what's happening.
This is all just so cool. And I keep thinking, I'm going back to the LiDAR, because that is, you said superficial elevation, right? That gives you very accurate. If I have it correct, that is currently done with a plane?
Yes.
Is there any point in the near future where you see that that could be done with drones?
Oh, yes, it is being done with drones. Yeah. So it depends on the scale, obviously. If you're going to do the whole state, you're going to do a plane. But plenty of people are doing it with drones. Or, I mean, you can even scan just a single outcrop and get very high resolution data on the outcrop. I think the sensor itself, of course, the price is coming down. And so more and more people are doing this.
Is there any technique that allows for, like ultrasound has totally transformed medical imaging? We no longer just get an X-ray. There's all sorts of things. I'm curious, do you know of any research being done? And not only am I over my skis, I'm asking you to talk about something you don't do. So this is a great conversation for you.
It's great.
Is there any way that people are looking into how to do similar measurements with what you're doing with the gravimeter, but from drones with penetration? I guess what I'm thinking of is a million years ago when I was first out of school, I did environmental consulting, and one of the people on one of the projects we were on was doing ground penetrating radar, which was really cool, right? But also unwieldy, expensive, super specialized. And I'm just curious, how far along have we gotten in taking some of the other tools that other fields have used? And is that applicable in geology? Or are we just not even close to it because of the fact you're trying to get through rock?
No, I mean, there are so many advances, people using drones to do geophysical work in geology. I mean, again, I'm not a geophysicist, but there's definitely huge advancements. For the most part, for me, they're all too expensive because I don't really have a good budget. But when you look at colleges and universities, right, where you can spend, and these are actually ridiculously low amounts, right? Like $5,000. I can't afford that, but a college can, of course. Like they often have that kind of money. And so we're not talking about hundreds of thousands of dollars. We're really talking about just a few thousand. But even within Maine, like our colleges are using drones to do this work. People still do a ton of GPR. It's actually quite inexpensive to do that work. I don't personally do it because that doesn't tell me anything about the rocks. That's more superficial. So a lot of the techniques have more to do with superficial. I mean, that's really important in Maine, right? You can tell a lot about the water, where it's going, what's in the water by these different techniques. And again, about depth to bedrock. That's important for depths of sediments, what kind of sediments there are, the structure of the soil, things like that. So there's certainly huge advances. And using drones has been amazing, even just for photography, especially the coastal group, or they're using drones to access those hundreds of miles of coastline that you wouldn't really be able to look at efficiently walking or on a boat, but you can fly a drone, and you can fly a drone repeatedly, right? Which is the power of that. So you can see change. Our coastline is changing very rapidly, and using drones to image that is extremely useful.
What's the most surprising thing that you have learned about Maine's bedrock in the time that you have been at the survey?
We have been making so many discoveries lately, and I think I'm always shocked that we just didn't know these things before. So my colleague at the University of Maine at Presque Isle, Dr. Chunzung Wang, he's been working in northern Maine. And that area was mapped, again, in low detail in, say, like the 60s and 70s. And his detailed work is really just completely rewriting the geologic history of that area. Part of that is, yes, he's going to more places than these people were able to access, for sure. But the other part is that the theory of plate tectonics really wasn't accepted until the early 70s. And so when those geologists were mapping before that time, the way that they understood the rocks were completely different. And so a lot of this has persisted in Maine geology kind of up until now. You know, we think we understand these structures in the rocks and how they were assembled. But with fresh eyes and our new theories, I mean, plate tectonics is not new, but in Maine, sometimes it feels new. We're really changing the model of how we think Maine got put together. The more we do dating of rocks, so we separate little minerals from a rock called zircon. They are extremely resistant to weathering, and they contain uranium, which breaks down to lead over long periods of time. And so we can actually date those little crystals. And the more that we do that, I think the more that we find our hypotheses of the ages of rocks have to change. I mean, even I dated a granite in the Lewiston area, and it was assumed that it was a bit younger than it turned out to be. So it turned out to be like 420 million years old. And I think people assumed it was probably closer to 400 or 390. And even just that changes our understanding of the rocks and their history. So yeah, I think that's quite surprising, is that we're still doing this. We're still making huge discoveries in the bedrock every day.
Those numbers are almost hard to comprehend.
Yes.
Do you have a favorite part of the state geology-wise that you like looking at or exploring?
You know, I really like down East Maine, and I haven't done any professional work there, but that is where we vacation every summer. And every time I see those rocks, I'm like, I wish I could come back and work here. And maybe eventually I will make it such that I can do a project out there. Mostly I'm in the Lewiston area working kind of central Maine, but I love those rocks. A lot of them are volcanic. So they came out of volcanoes, again, hundreds of millions of years ago, but they still look like volcanic rocks. So that I find really interesting. I think because mostly I work with rocks that have been changed by pressure and temperature so much that they're not recognizable as the original rock. And that was my area of study. I was a metamorphic petrologist by training. So I looked at rocks that went through changes from pressure and temperature. But the rocks down east, they still look like volcanic rocks. And to be honest, they're pretty. They are purple, a lot of them. They are just interesting. So I think I like that area, and I would like to work there.
How do those compare to what you saw in New Zealand?
Oh, yeah, they're kind of similar. The New Zealand rocks would have been younger, but yeah, kind of similar, right? Like they came out of a volcano and they look like volcanic rocks. That's true. I never made that connection. That's interesting.
Yeah, my dad was a geologist, and it was fascinating to go down east and have him talk about volcanic rocks. So I totally get why that would be interesting. I could keep talking to you for hours and hours and make you explain your work more and more, but what that means is that we'll have to talk again as you get your gravity measurements going.
Oh, yes.
And explain more about that project. I do want to circle back to one other question. Early on, we talked about how what you do is a true public service, and what the work that the Geological Survey is doing is available for anyone to use. I'm curious, do you have examples of how people, industry, educators, whatever, use the survey data to do whatever? I think connecting that dot would be really helpful.
Yes. Actually, when we apply for our grants, we usually need to supply these examples. So we do actively seek them out, ask people to let us know. But anything the Department of Environmental Protection, anything that they do, any type of site assessment has to start with the basic mapping. Because you need to know what's there before you think about how it's going to be impacted by anything, or how it may have been impacted, or how the water is moving through the rocks or through the surface materials. And so anything they do has to start with our maps. And we often help them kind of locate and download that data. All of that data is available for free on our website. Anybody can access it. But sometimes it's nice to talk to somebody who's familiar with it. And so we can just say, yeah, you need this map, you need that map. So we do that a lot for our colleagues in the DEP. The DOT, so the Department of Transportation, again, anytime you're doing bridge construction, road construction, you want to know what you will be finding under your feet, or you're trying to find material to help you build that road, right? It makes more sense to get material locally than try to ship it in from somewhere else. They can find that information on our maps. We work a lot with our academic partners. When you're looking to really dive in to study the rocks, you kind of need to know where they are. And so our maps do that. I often work with my academic colleagues to just kind of go and do field trips and point out rocks to them, right? Like these rocks that you're interested are here. And we know a little bit about them, but it's always so fantastic for someone to take an in-depth look at whatever aspect is their field. So that might be microstructure, really digging into the little piece of rock and what exactly is happening in it, or it might be geochemistry, or it might be looking at ages. It might be looking at those zircons in detail. So I do that. We have a water well database that we maintain. So anyone who has a domestic drinking water well, which is more than 50% of our population, those wells get reported to us. And what that means is any driller who's drilling a new well can look in our database, and they do, and they tell us this all the time. They go and look and say, okay, I'm going to be drilling at this house. What are the surrounding wells? How deep are they? What are their yields? And so it can really help them site a new well. And that's probably one of the most useful and probably most used pieces of information that we provide, is really looking at the water well database. There's also just general interest. We often have people just come in and want to see the maps. They just want to know what the rocks are. They're just interested generally in geology. People bring in rocks for me to identify. I'm constantly disappointing people that they did not find a meteorite. It's really sad. Someday someone's going to bring me one, I swear. But mostly I break hearts left and right. But, that's also a way that people use our information, is just to learn about the world around them.
Who do you apply to grants? Like, who's the granting agency or foundation?
So for my work, it's mostly the U.S. Geological Survey. So there's actually a law that says they need to work with us to fund basic geologic mapping. The Mapping Act was first passed in 92, and they just keep renewing it on whatever their schedule is. I forget. Every 10 years or so. So for mapping, mostly we go through the USGS. Our coastal counterparts, I think, mostly go through NOAA to get grants to do their work, mostly federal grants.
That makes sense. I just couldn't imagine the state was making you apply for grants as a state agency. So I just wanted to make sure I had that right.
Oh, yeah. I mean, most of our work is grant funded. Yeah.
Amber, I think what you do is really cool. I think it's a really great reminder of the value and the importance of basic research in a way that doesn't necessarily at the end of the research have a dollar sign, but that does not by any stretch of the imagination limit its importance. And I am personally grateful that you were willing to let me take up some of your time this morning to talk about the work that you're doing, because I think it's really easy for most of us to forget that there's really valuable and important research happening at the state government level. And any chance to have that reminder, I think, is really important. So I appreciate your time and I appreciate your work.
Thank you so much. Yeah, I agree. There's a lot of us in state government, in federal government, that are just working for you, for the taxpayers, and trying to get high quality scientific information out for people to use and to make their lives better.
No better place to end than right there. Thank you.
Thank you so much.
Thanks for listening to the Maine Science Podcast. Make sure you never miss an episode by following us on your podcast platform of choice. And please leave a rating and review. It will help more people find us and help spread the word about some of the remarkable people doing science in Maine. The Maine Science Podcast is recorded at Discovery Studios at the Maine Discovery Museum in Bangor, Maine. The Maine Science Podcast is executive produced and hosted by me, Kate Dickerson, and edited and produced by Scott Loiselle. And the Discover Maine theme was composed and performed by Nick Parker.